Welcome students to the second lecture on the MOOCs series of lectures on statistical inference. In the first lecture, I have given a brief introduction to what statistics or in particular statistical inference means to us, and also I have revised some very popular and commonly used probability distribution. Among them, in discrete we had binomial, Poisson and geometric distribution. For continuous case we have used or we have learnt normal, uniform, exponential and gamma distribution. We will be using them in future. In today's talk, I will give you some brief idea about sampling and sampling statistics. We know that the inferential statistics is all about learning about a population from a sample. At this juncture, I like to distinguish between two terms, parameter and statistic. A parameter associated with a population So, this is a property of the population, we can say. For example, if you are considering the annual income then its average over the population is one parameter. That is a population parameter that is fixed, but often this is unknown to us, and the whole purpose of inferential statistics is to understand the population parameter on the basis of some sample. So, samples are used to infer about population parameter. In order to do that, appropriate values are taken from the sample and some function is applied on those sample values Such a measurable function is called a statistic. The name is given by Fisher. So, we have a population, we want to know about some of its parameters. We have taken a sample. From those sample observations, we have measured certain values and applied a function on that one in such a way that from that function value we can get an idea about the population parameter. Such a function of the sample values is called a statistic. Okay? It must be noted that statistic is also a random variable. For illustration, suppose 100 students are there and I want to know the average score of the students in statistics. So, what we do, suppose we have taken a sample of 10. So, suppose this is the entire population and we have taken 10 samples out of it, and suppose like that 10 samples are taken and suppose I compute the statistic. Why this is a random variable? Because if I repeat the same experiment, it is not mandatory that I will be selecting the same set of samples. Now, I will be selecting maybe some different samples and therefore, I compute its corresponding statistic. It is clear that if there are 100 students and I take 10 out of it, then I can get 100 C10 so many different samples. Each one of them will produce a statistic. This is the statistic that I am going to use to estimate the population parameter. However, this statistic is random, as there can be as many as 100 C10 so many different statistics. Therefore, it makes sense to talk about the distribution of that statistic, which is called sampling distribution. In today's lecture, I will be talking about some sampling distributions, which will be helpful in estimating population parameters. Before that, sampling strategies. Depending upon the purpose, different sampling schemes are devised. First of all, it can be probabilistic or non-probabilistic. Let us focus on probabilistic sampling. The simplest form is simple random sampling. In simple random sampling, which we often write as SRS, all the units of the population have equal chance of being selected in the sample. It is sometimes difficult to design and time consuming to execute, but it is very simple in understanding and it gives equal chance to all the members of the population. Simple random sampling is useful when all population members or all population units are similar in nature. But in reality, that need not be true. For example, consider exit polls. There are so many voters in terms of millions of voters scattered all over the country in different states, different districts, different blocks, different polling booths. It is impossible to consider all of them with equal probability. So, what can be done? If this is the country, we can break it into different states. We may choose some of the states randomly. Within those states, there may be many districts. Again, it is not possible to consider all the voters of one district. So, what is done? Suppose some of the districts are chosen randomly. Then within a district there may be different subdivisions. Within the subdivisions there may be different blocks. Within each block there may be several booths. Within each booth there may be several voters. We need to take the opinion of some of these voters to predict what is going to happen. Therefore, giving equal probability to all the members or to all the voting population of the country is impossible. So, what is done? The population is divided into different stratum, right. At each level it is subdivided into lower order stratum like that until we reach to the very basic units, and from whom the actual data has to be collected. Such a way of sampling is called stratified sampling. Another way of sampling is called cluster sampling. For example, we are making an economic survey on the population of Delhi. Delhi has a huge population, but the problem here is all the elements of that population are not somewhat homogeneous in nature. In fact, they are highly heterogeneous. Therefore, application of a simple random sampling will lead to very erroneous result or a result with a huge variance, because the outcome of the survey will be very different based upon the samples that you have chosen. Therefore, it is more meaningful to divide the entire population into different clusters such that the clusters are homogeneous in nature. Say for example, this may be a cluster of people with very high income, this may be a cluster of very low income, this may be a cluster of say middle level income. Therefore, choosing the sample over the entire population randomly, first we divide it into some clusters which are more homogeneous, and then depending upon the size of cluster we can decide how many samples will be taken from each of the clusters. By sampling in such fashion is called cluster sampling. Similarly, there is something called systematic sampling. It is a mixture of strategies. So, first the units are arranged linearly. Say by sorting them according to their names. Then instead of applying a simple random sampling over the entire population, one of the starting point is randomly chosen over the entire population. After that, the members are chosen according to some fixed interval. This is also very useful technique for sampling, as it is much less time consuming and costly in comparison with a simple random sampling. So, in today's class we will be focusing on simple random sampling, which again can be subdivided into two ways: simple random sampling with replacement and simple random sampling without replacement. In short, we call it SRS WR, and this is called SRS WOR. What is the difference? The difference is as follows. Suppose x1, x2, x3, xn is the population. And we take a sample x1, x2, xn, where n is much less than n. If after taking one sample, we put it back again into the population before choosing the next sample, this is called simple random sampling with replacement. The sampled unit is put back into the population before taking the next sample. On the other hand, in SRS WOR, once a sample is taken, it is not considered for next sampling. Therefore, in SRS WOR, one individual unit can be represented only once at the most in the sample. On the other hand, in SRS WR, theoretically, in all the n samples, there is a possibility that you can choose only the same element small n number of times. Therefore, let us look at what is the distribution of the first sample. So, you have x1, x2, xn as the population. X1 is the very first sample taken out of it, and each one of them has equal probability. So, it can be x1 with probability 1 by n, it can be x2 with probability 1 by n, and it can be xn with probability 1 by n. Therefore, what is the expected value of x1? Which is equal to the population mean. Let us denote it by mu. Therefore, the first sample has expected value equal to population mean, that is irrespective of whether it is with replacement or without replacement. Now, let us look at x 2. Under SRS WR, so if you are doing simple random sampling with replacement, then whichever element has been taken in the first sample or as the first unit of the sample, it is put back into the population again. So, for SRS WR, again I have all x 1, x 2, x n, and they are all equally likely. So, all of them will have the same probability 1 by n, 1 by n up to 1 by n, and therefore, expected value of x 2 is equal to again 1 by n into sigma x I is equal to 1 to n is equal to mu. But now things change with respect to SRS WOR. So, what will happen in this case? What is, let us look at what is the probability that x 2 is equal to x k, fixed k, right. Say, what is the probability that the second unit taken as a sample is actually the kth member of the population. So, probability x 2 is equal to x k is same as probability x 2 is equal to x k, given that the first sample is equal to x j, j not equal to k, multiplied by probability x 1 is equal to x j, right. And this we need to sum over all j, j is equal to 1 to n, j not equal to k, because it is without replacement. Therefore, second sample can be x k if the first sample is something different from x k, and given that then the second sample is actually x k, and this has to be multiplied by what is the probability of first sample is x j. For a particular j, probability x 2 is equal to x k given x 1 is equal to x j is equal to 1 upon n minus 1, because there are n many capital N many elements in the population. The jth one has been taken. Now, there are n minus 1 element. Out of this, we are choosing one element with simple random sampling, and therefore, all the n minus 1 of them have the same probability. Therefore, it is 1 upon n minus 1. Now, what is the probability x 1 is equal to x j? Probability x 1 is equal to x j is 1 upon n, right. Therefore, what we are getting 1 upon n minus 1 into 1 upon n, and this we are summing over j is equal to 1 to n j not equal to k. Therefore, actually we are summing it for n minus 1 times. Therefore, it is n minus 1 into 1 upon n into n minus 1 is equal to 1 upon n. If you remember, we have selected a particular x k probability that x 2 is equal to x k is equal to 1 upon n. Since k can be anything between 1 to capital N, each x k has equal probability of 1 upon n. Therefore, we see that whether we have chosen it with replacement or without replacement, it does not matter. The second unit that is being chosen also has equal probability of getting one of the capital N many units as the second selection. In general, probability x j is equal to x k or the jth sample is the kth individual of the population has the probability one by n. That is, each one of the original population members will have equal chance of getting selected in the sample at the jth instance for j is equal to 1, 2 up to n, because we are choosing n samples from the population. This can be shown in the following way. What is the probability that the j plus 1th selection is equal to the kth member of the population? So, this we can calculate in the following way. Probability x j plus 1 is equal to x k is equal to, consider the following. First, j samples have been chosen and I am looking at the j plus 1th sample. In the first j samples, out of x 1, x 2, x n, j have been selected. Since j of them have been selected, how many are left? We are left with n minus j units, right. So, in the j plus 1th instance, I am choosing a particular element x k. First of all, x k has to be here, it has not been chosen yet in the already selected j many samples, and now I am going to choose x k as the j plus 1th unit in the sample. So, that is of equal probability. Therefore, probability of selecting x k as that one is 1 upon n minus j multiplied by the probability that it has not been chosen at all, right. So, we do it in the following way. So, in the first instance, we can choose something other than the x k that has the probability n minus 1 upon n. Because out of n, one of them is x k, and so that we cannot select. At the first instance, I can select any of the remaining n minus 1 of them. In the second instance, therefore, what I will choose? I will choose one from among the remaining n minus 1, but not k, and that probability is n minus 2 upon n minus 1. Similarly, x 3 will have the probability n minus 3 upon n minus 2. And when I am selecting the x j, I have already selected j minus 1. So, how many are left? The number of elements left is n minus j plus 1. Out of that, I will be choosing one of them except x k. So, I have the selection possibility of n minus j of them out of n minus j plus 1. Therefore, what we are getting is that we have not chosen x k till the jth sample. That probability is n minus 1 upon n multiplied by n minus 2 upon n minus 1 multiplied by up to n minus j upon n minus j plus 1. So, this one has to be n minus j plus 1 upon n minus j plus 2 multiplied by, now that out of that n minus j element I am choosing x k, that probability is 1 upon n minus j. So, what we are getting? These terms cancel each other, and what we are left with is 1 upon n. Therefore, even at the j plus 1th stage, the probability of choosing x k is equal to 1 upon n. Therefore, it suggests that all the elements have equal chance of getting selected. In all the 1, 2, 3 or nth selection. What is the effect of it? The effect of is the following. So, we have taken a sample irrespective of SRS OR and SRS WR, each xi takes x1 or x2 or xn with equal probability one upon n. Therefore, expected value of xi is equal to x1 plus x2 plus xn upon n is equal to population mean is equal to mu, and this is irrespective of SRS WR or SRS WOR. Therefore, what is the expected value of sample mean? Which is x1 plus x2 plus xn upon n. We know that from the theory of expectation that expectation of sum is equal to sum of expectation. Therefore, expected value of x bar, which is the sample mean, as I already said that this is a random variable, is equal to expected value of x1 plus expected value of x2 plus expected value of xn divided by n is equal to mu plus mu plus mu. Therefore, expected value of sample mean is equal to population mean. Okay. Thus, we can see that sample mean can be used to estimate the population mean. Let us now consider variance of the population. The variance of the population is sigma square is equal to 1 by n sigma xi minus mu whole square. Suppose we want to estimate the population variance. Can we use variance of x bar for that purpose? Let us see. So, question is, what is the variance of x bar? As x bar is a random variable itself, this makes sense. Now, variance of x bar is equal to expected value of x bar minus expected value of x bar whole square is equal to expected value of x1 plus x2 plus xn by n minus expected value of x1 plus expected value of x2 Now, 1 by n we can take out as common. So, it is 1 by n square into expected value of x1 plus x2 plus xn minus expected value of x 1 minus expected value of x 2 minus expected value of x n whole square. We rewrite it as expected value of x 1 minus e of x 1 plus x 2 minus e of x 2 plus x n minus e of x n whole square. So, it is n terms and their square its expectation. This n terms square can be written as so, its square plus this square plus this square up to x n minus e x n whole square. So, this we can write it as x I minus expected value of x I whole square I is equal to 1 to n plus expected value of sigma over I sigma over j not equal to I x I minus expected value of x I multiplied by x j minus expected value of x j. Now, expected value of x I minus expected value of x I whole square is equal to expected value of x I minus mu whole square is equal to x 1 minus mu whole square plus x n minus mu whole square divided by n is equal to sigma x I minus mu whole square by n. This is nothing but the population variance, which is sigma square. Therefore, 1 by n square into sigma over I expected value of x I minus expected value of x I whole square is equal to summation over I sigma square divided by n square is equal to n sigma square upon n square is equal to sigma square by n. So, that is the first part of the expansion. The second part is 1 by n square into expectation of sigma over I sigma over j not equal to I x I minus expected value of x I into x j minus expected value of x j. Is equal to 1 upon n square sigma over I sigma over j not equal to I expected value of x I minus expected value of x I is equal to 1 upon n square sigma sigma So, this is giving us 1 upon n square into summation over x I x j, covariance of x I x j for all possible pairs I and j. Now, if it is a simple random sampling with replacement, then we can see that x I and x j, they behave in the same way. In fact, they are independent of each other. Therefore, if we are considering simple random sampling with replacement, then each of the covariance term will become 0. Therefore, we are left with variance of x bar is equal to sigma square by n if simple random sampling with replacement. But when we are using simple random sampling without replacement, this covariance will not be 0, because what we are getting in the jth term will depend upon what we have got at the ith time, and therefore, this will have some contribution. Therefore, the variance of x bar will not be sigma square by n, rather it has to be adjusted by a quantity. In the next class, I will start with this point and then I will go further with sampling distribution. Thank you so much.